Dear students, welcome to video 2 of our applied data analysis class. Today's topic is termed minimizing the cost function. The outline of this video is as follows. We first will reiterate major findings from the previous video and then hopefully understand that minimizing the cost function is not always an easy task. I will then provide you with a conceptually easy method that always ends up with a result. However, this so-called brute force parameter search is computationally extremely demanding and not very feasible for most inverse problems that you will encounter. We will therefore establish a much smarter way, at least for linear forward models, and this entails minimizing the cost function using partial derivatives. Okay, so let's briefly reiterate what we actually wanted to do. What we wanted to do is, we wanted to understand what was the mean trend of increase in atmospheric CO2 since the 1960s to today, and for this we found that we needed to fit a line to this famous Keeling curve. In order to do so, we defined the terminology of the loss function for very general forward models. Up here, this is the nonlinear case, and down here is if the case for a linear forward model. In both cases, you would define the loss function in a least square sense, meaning we want to minimize the misfit between our forward model and the observations using squared differences as an error metric. So how can we now minimize the cost function? Because once we minimize the cost function, we found the parameters that best reproduce our observations, which is the ultimate goal of all the inverse methods. Okay? So, for a very general forward model, I propose what I term the brute force parameter search. It's called brute force because your brain can take a break and the computer does all the work. What work needs to be done? Well, what happens here is we just guess model parameters, and for each guess, we calculate the misfit between observations and model, and then we take the best guess, which is the minimum misfit, as our optimized forward model. In the example of a linear regression, you can actually visualize that rather easily. So down here, this grid stands for the y-intercept and the slope of the linear regression example. So let's say slope is on the y-axis and y-intercept is on the x-axis, and every given grid box here corresponds to a certain pair of guessed y-intercepts and slopes. And for each of those guesses, we would calculate the misfit. And then this can be visualized, which is sometimes, not always, referred to as a heat map. And I've done this here for you. Note, this is not for the case of linear regression, because this you will do in the exercises, okay? This is a different case, but the principle is the same. So in this case, the forward model had two free parameters, and on the right-hand side, I calculated the misfit for each possible model parameter in the range that I investigated. So dark colors indicate a larger model data misfit, lighter colors indicate a lower model data misfit, and in this brute force attempt, I would just take the lowest model data misfit that I found, and I claim that this is my optimized forward model. Is this very smart? Not at all, but in some cases it works. However, not very many. So let's briefly discuss one problem of this method before we discuss all of them. Okay, so let's consider that I don't have a linear regression, but I want to fit a parabola. Okay, a parabola has three free parameters, one somewhat corresponding to the y-intercept, one to the slope, and then we also have an acceleration term over here. Okay, so we have now three free model parameters, and you see this brute force attempt becomes very, very quickly computationally challenging because the parameter space that you need to investigate grows and grows and grows as more parameters become available. Yeah, so even in relatively simple cases, and this kind of curve fitting approach is a simple case, even then you need to have a lot of forward runs in order to investigate the complete parameter space. And visualization of this becomes intractable in 4 dimensions. Even in 3 dimensions, it's actually comparatively difficult. But nevertheless, here, a minimum exists, and you could still claim you found the best model parameter, and this is your optimized model, and you don't need to take an applied data analysis class teaching you any fancier method than this. Don't be so fast. Fancier methods are definitely required. So let's briefly summarize advantages and disadvantages of this brute force approach. And first, I'm really happy because I think this is the longest take I ever had, and it's not that bad. So I will just continue. Advantages of the brute force parameter search: it's conceptually easy, and there is nothing you need to know about the forward model. All you need to do is evaluate the forward model. You also need no math skills whatsoever, just some computational skills with a lot of for loops, okay, investigating the parameter space. This is comparatively easy to code if you have some experiences, and it also always provides a result. However, you will never know if this is the correct result for two reasons. Actually, many reasons, but I will provide two here. First of all, you somehow need to claim what the range of parameters is that you investigate, and the minima of your optimized forward model may be outside that range of the parameters that you investigated. Also, it depends on how fine do you check your parameters, what is your grid spacing in searching the parameter space, okay? You could also be off by that, and you will never know if the solution that you found is correct. More importantly, it's a very slow method, and it's simply untractable if your forward model has even a medium complexity to it. So is there a somehow smarter way of how we can do this? And the answer is yes. There are many smarter ways, but all of them require some knowledge of the forward model. And in this video, we will now restrict ourselves to the case of linear forward models. If we do that, the cost function looks as defined previously, and we can now take another step back and assume that our cost function only depends on one parameter. If this is the case, we can imagine, remember, we don't know the cost function, we never do. If we knew the cost function, we didn't need any inverse techniques, okay? But we can imagine that the cost function has a shape as depicted in this plot down here. If our model only depends on one free parameter, I can illustrate this in this 1D example. So on the x-axis, I would have my free model parameter. On the y-axis, I have the cost. And I would like to find the location where the cost function is minimum, and this would then tell me what my optimal model parameter is. Now all your bells should obviously ring, because what this comes down to is finding extrema of functions. And this can be done using derivatives. Okay? Wherever the derivative with respect to the model parameter is 0, we either have a high or a low point. Okay? And we can use this to query the parameter space in a much smarter fashion than the brute force approach. So let's do this. We have to calculate these partial derivatives, which are not so easy, but I will go through this in detail, knowing that you will probably in an exam not be able to reproduce all that. That's fine, but you should in principle be able to follow along on what comes next. Okay, here it is, our cost function. And now we drop the assumption that our cost function only depends on one parameter. We do it in a quite general sense. And so what we want to calculate is the partial derivative of the cost function with respect to the model parameter ML. Okay, so I do this in several steps. And the first step is that I do apply the chain rule. So here is our derivative with respect to the model parameter ML. And what I do is I first recognize that I can apply the chain rule in order to deal with this square, okay? So I first calculate what is the derivative of something squared, and this is 2 times the something, okay? So this is the first step, and then I need to calculate the internal derivative of the something, yeah? And so it means that I draw the internal derivative into the sum. There's no problem in switching the order of sums and derivatives. And then I have to calculate the derivative with respect to the parameter f ml, and all these parameters are in the brackets. Which brings us to the second step, which then looks like this. It actually simplifies. Because what you should recognize here, this is a sum over all the model parameters. Those are just numbers in our forward matrix G. And so this entire sum collapses because in most cases the derivative with respect to ML will be 0 unless the parameter itself is ML, in which case the derivative is G with the indexes KL. Think about this for a little while, understand it, and then move on, because then we are here. So the sum over all the model parameters has collapsed, and we end up with this equation down here. And we will now go to the next step. So up here is the equation from the previous slide. What I do now is I move this GKL, again, those are only numbers, I move it into the bracket, okay? Those are only numbers, so I can change the order however I want. And this brings me to this equation down here, step 3, okay? So the JKL has now moved into this term and into this term. And now you remember what we actually discussed this morning, that I can describe a multiplication of matrix times vector or matrix times matrix with sums over the respective indices, okay? And so now you should recognize that here I sum over the number of model parameters and here over the number of observations. So this K corresponds to this sum over here, and you take a little bit of time and then you will find out that this term actually corresponds to the transpose of G times the data vector. And the transpose you can recognize here because those KL indexes, if I would flip those, then this is the standard representation of a matrix vector multiplication. Over here, something very similar happens. If this would be IK instead of KI, it would correspond to the matrix multiplication G times G. But because those indices here are flipped, we end up with identifying this term to be G transpose times G times M. This is not very difficult, but if you are not used to writing these matrix multiplications and so on in index form, then you may take some time to follow along. So I recommend you press stop, you think a little bit about it, and then you move on. I obviously move on immediately because I'm on a run here. And doing the partial derivatives now with respect to any model parameters brings us to what is termed the normal equation. This here is the normal equation, and those are the terms that we just identified previously. The only thing that I did is that I brought the G transpose D to the other side. Have we solved anything? No, we still didn't solve anything, but now we can solve it, because what you have to recognize here, that whenever you take a transpose of a matrix multiplied with itself, this matrix will be square. And if this matrix is square, then at least in theory, the inverse of this matrix will be defined. It does not necessarily always exist, but at least it's defined. And so then I can finally isolate our unknown model parameter by moving the inverse of this square matrix to the right-hand side. This inverse of the matrix is obviously not the inverse of G, which does not exist, but it's the inverse of G transpose G, and that's called the pseudo, I actually don't know how to pronounce that, I think it's pseudo inverse, in German it would be pseudo inverse, okay, of G. And believe it or not, This is the solution of our linear inverse problem. And there is only one solution, and that's the one. What does this mean in the context of linear regression? Let's just bring this back, okay? If you remember well, our standard form of linear regression, Gm equals D, would look like this. This is your G matrix, this is your model vector, and this is your data vector. And you know all of them. I mean, you know how to write them. The unknowns are obviously the model parameters, but all the rest is known. So nothing stops you of calculating G transpose G, of taking the inverse, of hoping that the inverse exists. It will exist in this case. Multiplying it again times G transpose, okay? Then including the observations over here. And then you end up with your model parameter vector, the slope, and the y-intercept. What a success. Remember, this does not only apply for linear regression, it actually applies for all linear forward problems. And so that's why you should, at least for this class, memorize the form of the normal equation up here and the solution of the normal equation, which is this one here. And this will be the baseline how you solve many of the linear problems in a least square sense. Maybe the ones who paid attention now have one question that remains. How do I know that we actually found a minimum and not a maximum? We only calculated the derivative with respect to the model parameter and set it to 0. With this approach, I find both maxima and minima. And so in the worst case, I would have found the worst possible combination of model parameters with the largest possible misfit to the observations. Obviously, this is not the case. Why is this not the case? You can recognize it here. It's because we are in the linear case. So however this sum here looks like for the specific problem, we don't really care. We know that the highest order of model parameters can be model parameters squared. There is no way to have higher order terms than that. And so the way you can imagine this is that, again, in a 1D case, if I have my model parameter here and the cost function here, it will have a somewhat parabolic shape. I don't know the exact shape, but it will have the form of a parabola, something like this, okay? And the parabola only has one minimum. There is no maximum or anything else. And this is another takeaway. If your forward model is linear, first of all, you only have one solution for the least square sense, and that is given by the normal equation. And this solution will automatically also be the minimum. There is no need to check for any second derivatives and inflection points of the cost function. This can be illustrated, for the case of linear regression, with a brute force attempt, and here this is done. Imagine here are your two free parameters, y-intercept and slope. Now they are called theta. Previously they were called m. I just blatantly stole this plot from the internet. Apologies from that, okay? Feel free to do your own nice plot and then give it to me for the next version of this lecture. And here is the cost function, now illustrated in a 2D case. And you see this parabola shape, okay? And the minimum will be somewhere in here. And there will be only one. So what are the takeaways from this lecture? You should memorize 2 to 3 things at least. First, finding the minimum in a general loss function is a very challenging task, and it crucially depends on the nature of your forward model. The most primitive approach to finding this minimum is a brute force attempt, where you just sample the parameter space as good as you can, and then you take the minimum misfit that you come up with to be your optimized forward model. There's a number of problems linked with that approach. One of them is computationally very demanding. If you have a linear forward model, then you go memorizing the normal equation, and this gives you the solution for this particular problem, and there's only one solution. There is a catch to it, as always, as I told you, depending on the problem, the pseudo-inverse does not always exist, okay, and we will dive into that in the following lectures. But in the case of linear regression, it surely does exist as soon as you have more than 2 observations. If you have only 1 observation, it's obviously difficult to fit a line. There's many solutions that, but if you have more than 2, you should be safe. And this will be also part of the exercises to come. Thank you very much for listening. I'll now cut this video together, put it online, and I hope you enjoy it. Bye-bye.